Welcome everyone, wherever you are in the world. Thanks for attending this, the second series of webinars we've given at Asynt this year. Today we're going to be giving a brief introduction into photochemistry and really going to focus on more of how modern equipment, modern photochemistry apparatus has made the area of photochemistry a lot more efficient and a lot more accessible to chemists in modern laboratories. So it should be running about 35-40 minutes or so. If you have any questions along the way, please enter them into the Q&A section at the top of the Teams meeting, or we'll have plenty of time at the end of this session for questions and answers. So just let me share my slide deck with you. Okay, if someone from Asynt could let me know if you can see that.
Yep, that's all working.
Fantastic, thank you. So yeah, as I was, my introduction, I said we're really going to be focusing on a little introduction as to what photochemistry is and how it's impacting the industry and as us as chemists, but really focus in on how modern chemistry equipment has really enabled that rise of using these applications. So how do we initiate a chemical reaction? Well, hopefully I have enough chemists attending today that we all know how we can initiate our chemistry. We can do this generally, thermally, or by a chemical reagent, but there are areas of or techniques that have been underused over the years, and that's really been from the ease of use for the equipment setup, that inertia of finding the right apparatus and being able to carry out these lesser known chemistry methods safely and reliably and reproducible as well. So those two areas are electrochemistry, where we're using electrons as our reagent, and photochemistry, which uses photons and light. And these have seen really an increase in adoption over the last 10 years or so. We generally refer to these as reagentless chemistry. So we're also using these underused techniques in a more greener and efficient method as well. So we're going to focus on photochemistry, and this really enables us as chemists to activate some really challenging methods by conventional means. We can create some really complex molecules in a reduced number of steps, so we can reduce that synthetic route, including all of those workups and isolations, and get some really complex molecules. So if you're not familiar with photochemistry, it's really it's the branch of science that's concerned with the chemical effects of light, as it says in the title. In nature, it's the basis of photosynthesis, really life itself. We use photochemistry to see, and in the formation of vitamin D from sunlight on our skin. So it's everywhere. Photochemical reactions really they proceed differently from those other techniques that really give us some access to some unique chemistry. And as we're using photons as a reagent, it's cleaner and therefore a greener method as well. And we'll cover some of that as we progress. So essentially, and I'm not going to go into into too much detail, but when a molecule absorbs a photon of light, its electronic structure changes with different activation stages within our compounds. And then it proceeds to react with other molecules. But each molecule or moiety, structural functionality, requires a different wavelength. So we really need to be selective in the wavelengths that we irradiate our reactions with to have some specific chemical pathways. So we need to have, ideally, a discrete wavelength, a single wavelength, to proceed with any kind of control over our reaction conditions. And modern chemical apparatus allows us to do that. Here I really wanted to show the increase in adoption of photochemistry methods. It's gained lots of popularity over the last 15 years or so, and that's really come from the commercial availability of photochemical reactors. When I started looking at photochemistry, we were using homemade systems with mercury pressure lamps and immersion cells with tubes wrapped around them. And while they're relatively easy to set up, we lose some of the safety aspects. We have potential increase in ionizing energy sources, that high powered light source from mercury pressure lamps that we really need to protect ourselves from. Modern chemistry and modern photochemistry reactors have better temperature control and better shielding and safety from that ionizing radiation. So that's really helped drive the increase in adoption of photochemistry, but it's also increases our chemical space. We can develop novel synthetic routes, reducing the number of reaction steps, as we've discussed. And those modern photo redox catalysts that are being developed allows us to move away from UV light sources, those shorter wavelengths, to visible light, which opens up lots of possibilities for safety, but also for apparatus use. And it's also that awareness as photochemistry as potentially a greener chemistry. And that's really a key driver in lots of industries to make ourselves more sustainable. So many of you will be familiar with the principles of green chemistry. These principles have been around for decades, and it drives lots of the approaches, especially to manufacture of API, for example. But focusing on two elements of this webinar today, that being the development of new light sources, so that being LEDs, and also the advantages of new reactor designs, enables us to really access some of these green principles. We can have better selectivity, improved reaction efficiency, better temperature control, and improved design allows for higher photon flux, which means that we can potentially increase the reactivity rates of our reactions. So we're preventing, even with just those two elements, we're preventing waste. We've got better atom efficiency, less harmful chemical synthesis, and a design for energy efficiency. Photochemistry really potentially hits every single one of those green principles. And I'm not going to go into this in any detail. This webinar is recorded, so we can go back and look at this in more detail. But we can reduce hazardous reagents for in that prevention of using difficult to handle and scalable reagents. We have better atom efficiency, less hazardous chemical synthesis. We can design for safer chemicals. We can be more selective in the activation of molecules and design novel reaction pathways. We can reduce the harmful oxidizing or reducing reagents that we use. We can be better energy efficient, and on and on. So you can see photochemistry really impacts us in a cleaner, greener, more sustainable approach. And I'll allow you to read these later on the recording. So I wanted to just give you a brief history of photochemistry, because this technique's been around for hundreds of years. So where did it really begin? So looking at literature, I would kind of argue that this example here is probably the first cited example of photochemistry. So this was done by Transdorf all the way back in the 1800s. And he observed how crystals of this sequestropine santorin molecule, when he shined a light on this, that the crystals burst. Now, this was later explained that this multi-step photochemical reaction causes a dimerization of this compound, and that increased volume led to that crystal volume increasing, and the crystals bursting. So this is probably one of the first examples of photochemistry that was cited. But photochemistry has moved on over the years, and there's 3 examples here that I picked out. One from Eaton in 1964, looking at cubane synthesis. The second one from E.J. Corey, again in the 60s, and that's looking at a retrosynthetic approach to carry out the synthesis of these corallophyllenes, and Wender's synthesis of cedrine here. And you can see they're all from a good 40 years ago. So this technique's been used for a while. But what you can see from these reaction schemes is that from relatively simple starting materials, we're building incredible complexity in a very small number of steps. And that's where photochemistry on small molecule synthesis can really help us. Developing that complexity in reduced synthetic routes. So what are the advantages of photochemistry to us as chemists? There's lots of advantages, not just from those green potentials, but modern photochemistry equipment and those unique designs allow us a versatility in scale, but also methodologies. So access to both batch and flow photochemical reactors allow us to optimize and explore method development under batch conditions, and then potentially use flow methods to scale. And we have customers that are working in tens of kilograms on large, high-intensity photochemical reactors, continuous photochemistry reactors. So the increase of using LEDs as light sources has enabled us to have very narrow emission bands for better selectivity, also reducing heat, which is key for controlling our reaction temperatures. We have efficient light transfer. So we have light sources that are designed to focus photons specifically into our reactors to increase efficiency. We have increased safety features. So we have interlocks and fully light enclosed reactors. And when we're using high intensity, lower wavelength light sources, this is really key to protect us, because that ionizing energy can be quite harmful. We can have precise temperature control, so we can separate the heat produced from our light source to our reactor, and that's really key for selectivity. We can use parallel reactors for optimization approach. We can use continuous photochemistry in an automated principle, where we can run series of reactions to look at different substrates, different chemical space, for example, to make arrays of compounds. And because we're using LEDs, we can have customizable wavelengths. Most modern LEDs come in about 20 nanometer divisions. So we can be very selective, and we can choose the wavelength on our photo redox catalyst, for example. So let's think about light sources, because this is really key to the development of modern reactors. So in the past, we would have used mercury pressure lamps. That was historically what we used. And these are generally high intensity. But also what they give is a broad spectrum of wavelengths. And you can see that emission spectrum there from a medium pressure mercury lamp. There's no selectivity or it's difficult for us to select the wavelength of choice. Now we can use filters, for example. We can use long pass filters to block the shorter wavelengths, or we can have bandpass filters to be more selective and filter out certain wavelengths to get to the wavelengths of choice. But it's very difficult to get monochromatic light sources from these lamps. They also produce a lot of heat. They're incredibly energy inefficient. So they also need external cooling. So if we're using a 150-watt mercury lamp, we need a very efficient cooling system to be able to separate that energy, the heat we're producing from the light source to the reactor. Now, LEDs and the advancement of LED technologies has really opened this technique to more targeted photochemistry. As I said, they have a very narrow emission bands. I would say they're pseudo monochromatic because there's still a reasonable bands of spectra, but they are more or less monochromatic. LEDs also have a smaller radiation window, as we said before, and allows us to be really targeted with lenses, if necessary, to target directly onto the reactor. Now, I've said flow reactor channel there, but also on within our batch reactors as well. And they give off less heat, so we don't need as much cooling. Sometimes we don't need cooling at all. So if you compare traditional mercury lamp technology to LEDs, we can be more selective. We have better temperature control, better selectivity, certainly better safety, and just better cooling. So some of the advantages of the light source there. If we look on the left, so that's showing, so mercury lamps, we can have low, medium, high pressure, and they give different emission spectrums. So the low pressure lamps, we can be necessarily monochromatic, but in that UV region. When we start to go up into the visible light source by increasing the pressure of the lamp, you can see we start to increase that range of wavelengths. So we have a broader spectrum of emission. If we look at the table on the right here, you can see that with modern LEDs, we can cover the scope of those medium pressure mercury lamps. So we're able to access most of the emission spectra and be very selective in the wavelengths that we choose for our chemistry. If we now focus on the reactor, you can see that there are limitations with using photochemistry, with using light. So one is the Booger-Lambert-Beer law, or the Beer-Lambert law, as it's most commonly known. This essentially tells us that the further away our reactor is from the light source, the less energy we have. The photons lose their energy very, very quickly. In the range of millimeters away from the light source. So we really need to design our photochemical reactors where we can get light into our reaction as efficiently as possible. Now, when we think about using traditional round bottom flasks, that means we're only really illuminating from on the outside edge, unless we can put our our light source directly inside, which is what we explore with the Asynt batch reactors. But as those reactor volumes get smaller, for example, with flow reactors, where we have, for example, a 1 millimeter capillary, that light penetration is a lot more efficient. So we can design our reactors for different applications, but also for more efficient irradiation. And that enables us to have better with more energy going into our reaction, more photons going into our reaction, which can also help us with selectivity, less side products, because we're not having any masking or any concentration gradients that will give rise to byproduct formation, a lot more efficient. And also, if we have more photons into our reactor, we can potentially reduce the reaction times as well. So we need to think about reactor design. We also need to think about the material of construction. So certain material can act as a wavelength filter. So we need a material that's transparent to our wavelengths of interest. So you can see on the right here that glass is a very good transmitter, or allows good transmission of photons into our reactions. but it will cut off at some point. If we use photochemical reactors, we can then start to look at perfluoropolymers. And some of these are incredibly transparent to even UV wavelengths. So things like FEP tubing, you can see it has a cutoff about 180 nanometers in wavelength. So we can mix and match. We can use both glass and perfluoropolymers to design reactors that allow very good light transmission into our reaction. We also need to think about reaction scalability as well. So once we've optimized our conditions, found the right photo redox catalyst, found the right wavelength, found the right temperature, we need to be able to, or in some instances, be able to scale this. And that's really where the popularity has suffered. And it's that initial limitation to its scale-up potential. So as we've said with the Beer-Lambert law, our photon energy decreases rapidly. So if we want to scale up our reactions under batch conditions, we're only still illuminating or irradiating the outside of our reactors, and then the bigger the vessels get, the less efficient that is. Now that's where flow chemistry can come in, where we have better transmission into our reactors, and in a continuous experiment, we can just leave our reactions running for longer. So that scalability under batch conditions is slightly limiting, but there are methods to mitigate that. So when we scale a continuous photochemistry reaction, we're looking at a number of different strategies, and these are similar to how we would scale up a traditional flow chemistry experiment. So we can increase the throughput of the reaction by just leaving the reaction running for longer. Then we're not having to change any of our reaction conditions. We can scale out. We can use multiple reactors that will still see the same reaction conditions, but enable us to increase our output. If we increase the radiant flux, the intensity of our photons into our reactor, we can potentially, as this is the reagent, decrease our reaction times as well. So having a photochemical reactor where we can change the intensity, or we have access to increase wattage, increase light intensity light sources, enables us to optimize on smaller scales, but then also increase the light source to increase our throughput and scalability of our reactions. Which is what's mentioned here. So increasing that light intensity in the same reactor can potentially reduce our reaction times, and then we can speed our reactions up and create more material. Really nice examples of these in the literature. So I'm not going to run through any chemistry today. This is really just an introduction to photochemistry and modern reactors, a cursory look at photochemical reactions on any search engines will give you some excellent examples, and we may cover that in another session. So the take home here is that flow reactors, although they might not change the efficiency of our photochemical reaction, are able to deliver, in examples, quite a high increase in our throughput compared with the equivalent batch reaction. So it's a really useful technique to run parallel with traditional batch photochemistry methods. So I've highlighted some of the advantages of continuous photochemistry using flow reactors. Flow chemistry does give us some advantages over traditional batch techniques, and then adding a light source into that equation gives us some further benefits as well. So we've spoken about the improved irradiation of our reactors, so we can improve that light transmission into our reaction. Scalability is a key element in this equation, both with the light transmission and the ability to run our reactions continuously. Selectivity really covers both techniques. Single LED wavelengths help us get to that controlled reaction pathway. Reproducibility is interesting. In a batch reactor, we're running under kind of turbulent conditions, which means it's really difficult to repeat the batch conditions exactly. We have concentration and thermal gradients and a radiation light gradients in this example. Flow chemistry techniques give us that reproducibility. If our reagents and our equipment are reagents are the same concentrations and our equipment is exactly the same, we'll get reproducible chemistry. There'd be no batch to batch variations. And that can be really key, especially in production methods. Flow chemistry lends itself really well for better mixing and heat exchange. That goes hand in hand. The ability to perform multi-phase chemistry is another advantage. If you think about running, for example, reactions with gases under batch conditions, we generally use bombs. We use vessels that we can pressurize, and they're generally made out of stainless steel, so they don't lend themselves very well to running photochemistry reactions unless we have our light source internally. So that can be really tricky, but flow reactors are typically smaller volumes, easy to pressurize. So that gives us access to photochemical applications like photooxygenations, for example, where we can add our reactive gases and illuminate them at the same time, irradiate them with our light source. And then safety comes into the whole question as well. So I guess the question is, we've covered, or we've spoken about different reactor technologies, whether it's a traditional batch reactor or a flow reactor, and having access to both gives us the widest opportunity to run the chemical application that we want to carry out. So when would you choose one over another? There's a few factors we need to think about. So one is homogeneity. So flow reactors lend themselves very well to having our reactions completely in solution. That's their sweet spot. If we've got any kind of solid material, whether that's an inorganic base or a heterogeneous photo redox catalyst, then traditional batch methods will always be more favorable. They can tolerate solids. We can have even a highly viscous material and have high torque stirrers that can handle solids. So when we have a solid material, batch reactors will always be the chosen methods. Now, CSTRs, or continuously stirred tank reactors, are used lots in flow chemistry applications for handling light slurries and suspensions and for crystallization. So they can handle a certain amount of solids. We have CSTR reactors that we can illuminate with a light source, irradiate with a light source. I'm sorry, I keep saying illuminate. Whereas the flow reactors are good for scaling, but they really need homogeneous conditions. So the other question to ask is reaction time. Now, some photochemistry reactions are very dilute and take a long time. Some of them are just slow. We could potentially increase that with higher light intensities and more efficient redox catalysts. But if we've got a long reaction time, then batch methods will be preferable. Only because if we have long residence time or long reaction times under flow conditions, the throughput is a lot lower. So it depends on what we want to achieve, whether we want to achieve material for diagnostics, or we want to produce a larger quantity of material for other purposes. So long reaction times don't really lend themselves to an efficient flow process. As I said before, is one of our reagents a gas? So flow chemistry or flow continuous photochemistry is probably the preferable selection or technique to use when we want to add reactive gases into our reaction. Do we want to optimize our reactions or do reagent screening? So we have access to photochemical reactors that can have a single position, but can have multiple positions. The multiple positions, whether that's 8 or 12, and we have these that very efficiently sit onto traditional hot plate stirrers, give you access to explore different reaction conditions. Whether that's reagent screening, catalysts, concentration, for example. So they're really nice traditional methods where we get uniform irradiation of multiple reactor vials. That's a technique that most people are more familiar with. We can automate flow reactors and explore those different conditions, but that's another level of complexity. If you're familiar with automation with flow chemistry techniques, then that's accessible. But if we want to look at the basic reactor optimization or reagent screenings, those multi-position batch reactors might be preferable. Another question to consider is what's the scale of your reaction? Now, batch reactors are scale limiting, as we've discussed. The efficiency of the irradiation decreases as we increase the reactor volume. We've already discussed that a continuous process is readily scalable. So if we want to produce more material, there's no reason why we can't optimize in the batch conditions and transfer those to flow. So that's a consideration. How much material do we want to produce? What wavelengths do we want to use? Well, I guess the last two examples here are kind of neat because we have almost identical light sources for both the batch and the flow reactors. Under the Asynt range, we use the same LEDs with the Unisys products, exactly the same light sources. So wavelength selectivity really comes down to what wavelength you're using with your catalyst or your chemistry. Light intensity is a consideration. You might have a reaction that degrades under high intensity light. You might want high intensity for scale up and more efficiency. So having a system where, or the availability where we can choose the intensity of our light source, whether that's dialable, whether that's having a variable control to change the light intensity, or just access to low and high or low and higher light sources, really gives you the kind of the breadth of light intensity that you might need. So hopefully that's given you some kind of indication of where you'd want to go with your photochemistry reactors. Now, it would be remiss of me not to introduce some of our equipment. And I'm not going to go into this in too much detail. If you're interested in what we can do as a company, Asynt, in both batch and flow photochemistry, drop us a line, get in touch, and we can discuss this in more detail. But you can see under the batch photochemistry range, we have our lighthouse, which is a single or a free position photochemistry reactor system. The unique design of the lighthouse is that we transfer our photons directly into the vial rather than radiating from the outside, and that can really increase efficiency. And then we have a range of parallel batch reactor stations. The Illuminate, as it indicates, has 8 reactor positions, all with the same light source. The Solstice and the Solstice Maxi increase that to 12, from 8 milliliters with the Illuminate and the Solstice maximum reaction volume up to 20. So you could even use these systems for scale up. So a 12 times 20 milliliter concept for scaling up allows you to increase the output, increase the amount of material you're making with exactly the same reaction conditions without the loss of efficiency. So lots of techniques that we can employ here. And for flow chemistry, we have some really efficient reactors. As I mentioned, we can irradiate CSTRs, or continuous stir tank reactors. So you can see we have a light source, which is similar to the lighthouse, that enables us to irradiate our CSTR reactors. And then we have coil reactor, flow chemistry coil reactor based photochemistry equipment with the Borealis flow. The photo chip takes that approach of using a continuous process, but now using glass static mixers. And then we have the Photosyn, which was our first kind of venture into photochemistry. Now, the Photosyn can illuminate or radiate up to 700 watts. And this is being used quite extensively with customers for scale-up applications. Now, all of these products have very efficient temperature control. We can isolate the heat from the LED sources and also control our reaction temperatures precisely as well. So hits all of those sweet spots that we've been talking about. So I'm going to stop there for questions. I hope that's been useful, just to give you a brief introduction into some of the background in flow chemistry and how the development of modern photochemistry reactor design and LEDs really gives you that efficiency. So efficiency for better selectivity, improved radiation, better temperature control, increased photon flux, but also some of those safety aspects as well. So as you can see, we've got a whole range of products for any application. We have the expertise in-house. If you want to explore any of this further, please get in touch with us. And thank you for joining. And the next webinar is still to be defined, but I'll stop sharing my slide deck here. I think one of my colleagues can open up the mics, but if there's any questions anyone has, please feel free. I'm just looking in the Q&A. There aren't any questions yet. I think you should be able to unmute yourself. And if you can't, we'll see what I can do there. Yeah, I don't think the microphones are locked anymore.
A question. If the light penetration is on a very short distance, you could have a very high heating, even if the temperature in the reaction is low. I mean, let's say that all of the light is absorbed in, let's say, a tenth of a milliliter, then you would have a very high temperature on a very then you could have a very high heating, even though that you see a different parameter in the bulk of the photoreactor system. Do you have any way to measure it or to check it, or so we know which type of reactor we would like to have for a reaction?
I guess it also depends on the light intensity as well. I mean, if you're looking at tens of watts, then that's normal. So to remove that, the incident heat from the LED light source, you don't need any external cooling, just a simple fan to extract the temperature off of the LEDs. That's efficient enough, and with just internal fans to control most reactions in the tens of watts to 30, 40 degrees. So you don't really need any external cooling. But then you can couple the reactor with an external cooling source, whether that's a recirculator or some kind of cryogenic setting. So you can isolate the reactor temperature from the incident light from the light source and control that efficiently. And with a simple temperature probe, you can control that actively as well. With a capillary reactor, because you've got a higher surface area to volume ratio, it's a lot easier to control that temperature, because we can it's the heat efficient, or the transmission of our temperature control source is a lot more efficient. I hope that helped. I mean, certainly with the higher intensity light sources and the Borealis flow and the photo chip, we can illuminate up to 100, well, between 120 and 180 watts of power. So you really need very efficient cooling. And then we'd use a water circulator to take the heat away from the LEDs, but also using the equivalent recirculator or cryogenic based system, whatever you wanted to use, to control the reaction temperature. And that's very efficient, even up to 350 watts. We can control that reaction temperature all the way down to, I say 350 watts, maybe minus 10, minus 20.
Does the temperature influence the LED? I mean, does it in higher temperature, is it more efficient, less efficient, or it's not?
The higher the LED temperature, the less efficient it becomes. And it also decreases the lifespan, the lifetime of the LED. So you really want to be working about 70 to 80% of the LED power intensity, just to increase the lifespan. But you also want to control that LED temperature. So with the digital power supplies that we have with the high intensity lamps, we'd limit that LED temperature to, say, 50 degrees centigrade anyway. If it goes over that temperature, then we'd cut the light source. But even with just recirculating water, that's really effective. The design of the reactors allows that cooling to be very close to the boards that the LEDs are mounted on, and we can withdraw that temperature very quickly. I have some of the equipment behind me. If you want to drop me a line, I can show you that in more detail.
Thank you very much.
No, my pleasure.
We've got a couple of questions in the chat. So the first question we've got from Felix. How do you deal with darkening, fouling, clogging of heterogeneous mixtures in your flow chemistry setups?
Yeah. So you're always going to have some issues with the flow setups, which is why we offer both batch and flow. High intensity light can degrade the perfluoropolymers that we use over time. And you also see sometimes those degradation products building up on the inside of the reactor wall. And that can really, it looks like it's going yellow, but a lot of the time that's just a polymeric waste or byproduct that's forming. You can generally flush those out with DMSO. But if you have fouling in a flow reactor, then you need to adapt the chemistry slightly. And whether that's changing your acid or base source, decreasing the concentration, or maybe swapping to a continuous stir tank reactor that will allow you to generate some of that solid material as the reaction is proceeding, and still be able to cope with that flowing.
Thanks a lot. Do you know if the fouling is usually a photochemical, so radical-based mechanism, or is it a thermal mechanism that, like by the heat that is produced and then on the surface of the reactor wall or the flow reactor?
Certainly when you use high-intensity mercury lamps with that low wavelength intensity, then historically I have seen it being a polymeric issue with the actual the tubing itself. But with light, with visible light, that's a lot less frequent. You know, I mean, if you were running 700 watts through a PTFE tubing for, you know, an extended campaign, you might see some of that. Personally, it's more a chemical fouling that I've seen.
And so you can control it, sorry, last question, can control it by also alternating playing with the temperature, or is that usually not the case?
Temperature, intensity, solvent selection, concentration, just trying to adapt your chemistry so it becomes that that degraded material is more readily dissolved, and the flow system is able to continue.
Cool. Thanks a lot.
We do have another question in the chat from Alexander. Can we irradiate NMR tubes with any of these irradiators, photoreactors?
I don't see why not. Currently, we don't have a reactor that will, sorry, a reactor system that will enable to do that. The Illuminate is based on our Octo, so we could potentially design an insert to have multiple NMR tubes. Currently, we don't offer a solution like that, but if that's something of interest, drop us a line, and we can see what we can do to customize one of these for you, to potentially customize one of these. Okay. I can't see any more questions coming up. So again, just like to thank everyone for attending. I hope that's been useful. We've explored quite a few different concepts there. You obviously have our contact details because you're here. If you have any questions after this session, you can drop me a line and I'll answer everyone's questions. I know sometimes it can be quite intimidating to unmute yourself and ask in these situations. No questions is a silly question. And if you'd like to learn anything more about our range of photochemistry equipment, then also drop us a line and look out for the next webinar. And with that, thank you very much.
Thank you everyone for joining us.